Hello guys, nice to see you.
Hello.
Hi. Let's wait for 1 minute more, maybe more people will join. So I see that we have this decaying trend in number of attenders for the lectures. I guess maybe you can remind your friends that would be definitely beneficial for them to not to forget about lectures completely, because if this trend is going to continue for longer, there's a chance there will be just few students attending lectures. But in any way, who is interested, those are always welcomed. And if because of any reasons you didn't have a chance to go for online lecture, keep in mind that all lectures are recorded and you can find them on this Google folder where the course manual was posted, and there all recorded online lectures will be available, so you can always come back to them if you missed one or you want to double check something. Okay, good. Then I believe that most people who were planning to attend are already here, and we will start shortly from a quick remind of what we those concepts which we considered last time, and in particularly we describe the concept of Gauss law and like what it is, and today we will continue with some practical application of Gauss law, which can significantly simplify tasks for calculation of electric field vector for continuums of electric charges, where in those cases when there is some electric field symmetry present. So those cases can be really simplified a lot, and that definitely helps to solve this type of problems in a more simple and straightforward way. Okay, so let us change the camera. And last time we pretty much formulated the Gauss law, which can be written in such form, like integral over closed surface of a scalar product of electric field vector and dA vector. dA vector is nothing else as small area element of the closed surface times unit normal vector, which defines the orientation of this surface in space with respect to the electric field vector. And this integral is equal to Q internal divided by epsilon 0. So Q internal, it's charge which is enclosed in the closed surface along which we do this integration, and this is like mathematical form for this Gauss law, but let's also remind what it means physically. So we have shown that if we have a charge enclosed in some Gaussian surfaces, in other words, closed surfaces. So it's a cross section of a sphere, these dashed lines, or some random shape closed surface. It doesn't matter. The flux, the electric field flux, which is determined by this integral, is always equal to the electric charge enclosed by this surface divided by electric permittivity of free space epsilon 0. And also it comes out from this equation: if electric charge is located outside of a closed surface, its electric field flux through the closed surface is equal to 0, because if Q internal is equal to 0, so there is no charge inside this closed surface, then the integral of the product electric field dA is equal to 0. So in this case, electric field which is outside doesn't create any electric flux through the closed surface. So based on this fundamental feature of electric field flux through closed surface, we can proceed further and apply this statement, this condition, to solve particular problems when it is necessary to calculate electric field vector in a space point around, in a point of space around some continuum charge distributions. Let's go now to the next slide. And first example which we are going to consider will be the space distribution, like volumetric distribution of electric charge. Let's assume that we have some sphere with, sorry, it's not Q, with some volume density of electric charge, rho, and this charge is positive. Then this sphere has radius, let's call it A, and let us draw a cross section of a Gaussian surface, like closed surface, around this sphere. So our task is to calculate electric field next to this sphere with volume distribution of electric charge at a distance r from the center of this sphere. So as you see, this distance r is actually the radius of our closed surface, which we have drawn around the charge, spherical charge. So taking into account the fact that we have this spherical symmetry here, it is really makes sense to draw a spherical closed surface around this spherical charge. Now we will see how and why it works. So let's first write the electric field flux, like define it for this particular case. So in general, it will be, as we mentioned on the previous slide, integral over closed surface times d E vector times dA vector. So means that here we define some small surface element on this closed surface, and normal to this small element with area dA, normal vector n is directed like shown on the figure, and according to the symmetry of the electric field originated from a charge distributed in a volume of a sphere, electric field vector will be aligned in the same direction. So they will be parallel. And that helps us to get rid of these vectors on the integral, because cosine of alpha and alpha here, angle between E vector and N vector is 0. It will be unity. Then we can integrate over just product of two scalars. And according to the Gauss law, this law of like the electric field flux will be equal to the electric charge enclosed in the Gaussian surface, which will be Q capital divided by epsilon 0. So this Q capital is nothing else as our volume density of electric charge times volume of this sphere with a radius a divided by epsilon 0. So another thing which we need to take into account, that is actually also comes out from the symmetry of the this particular case. At every point of this Gaussian surface, the electric field vector amplitude, magnitude will be the same. So when we get this integral of E dA over the surface, we can consider electric field constant and take it out from the integral. So it will be E times integral over surface dA. And integral over surface will give us surface area of the spherical charge with radius a. In this particular case, it will be E times 4 pi. It will be the area of the closed surface, Gaussian surface, spherical Gaussian surface, which we have drawn around the spherical charge. So it will be 4 pi r square. And again, it's equal to total charge enclosed in this Gaussian surface divided by epsilon 0. So from this equation, we can easily calculate our electric field at distance r from the center of the spherical charge. In this case, it will be electric field equal to total electric charge in this sphere with a radius a divided by 4 pi times epsilon 0 times r squared. We know that Coulomb constant is equal to 1 over 4 pi epsilon 0, and that's why we end up with a final equation, electrical field at any arbitrary distance r from the center of this spherical charge with the radius a, and it will be equal to Ke, Coulomb constant, times Q capital divided by R square. And this is true when we specify that R, the distance at which we want to determine this electric field, is larger than the radius of the charged sphere. So this looks very similar to the Coulomb law, with the only this difference in Coulomb law is derived for a point charge. And here we have some spatially distributed charge with some volume distribution in the form of sphere. But when we calculate electric field created by such sphere of uniformly distributed electric charge, we can apply Coulombic law with assuming that all charge of this sphere with radius a is located in just one point at the center of this sphere. So quite simple result for this for the calculation of electric field around such a symmetric volume distribution of electric charge. Let us consider another example. And in this case, we will consider some infinite line, some infinite thread, which is uniformly electrically charged. So let's say we have this infinite line positively charged with some linear density of electric charge lambda. And due to the symmetry of this particular example, electric field lines will radially go in all directions from this electrically charged line. And that's why it is really convenient to consider some cylinder as a Gaussian surface. So let us draw some cylinder around this line. We have everywhere these positive charges. And in this, let's consider the height of this cylinder as L, and radius of the base of the cylinder as R. We can choose some small element on the surface of this cylinder with area dA and normal vector, unit vector n. In the same direction, because of the symmetry, will be electric field vector, E. Again, there is no angle between these two vectors, they are parallel, and that is very convenient for further calculations. What is really also important to highlight here, that if we consider some surface element on the edge sides of cylinder, normal vector will be perpendicular to the electric field vector. And in this case, our the electric field flux through the two surfaces at the edges of this cylinder will be equal to 0. That's why it is very important to select a right symmetrical surface for particular case in order to make our life easier and perform calculations in the most simple way. So that's why because of this orientation, we can neglect with two edge surfaces because electric field flux is equal to 0 and consider only the side surface of the cylinder. So in this case, electric field flux is also equal. So general equation is integral over surface E vector dA vector, taking into account that electric field vector and normal to the side surface is always, they are always parallel, and that at each point of side surface of this cylinder, electric field vector has the same magnitude because of the symmetry of this case, we can write the constant electric field over integral over the area dA. And this is actually equal to the product of constant electric field to the side area of this cylinder, and it equal to the total electric charge which is enclosed in this cylindric Gaussian surface. And which electric charge is enclosed there? We need to consider lambda as a linear distribution of electrical charge, and also the length of this, the height of this cylinder. So that's why total charge will be linear density times height of the cylinder. It's the length of the charge line which is enclosed by this cylinder divided by epsilon 0. And we know that side area of a cylinder is given as 2 pi r. It's length of the circle of the base of cylinder times height of the cylinder, and this is equal to lambda times L times divided by epsilon 0. From here, so we can cancel out this height of the cylinder, we get an expression for the electric field at any point next to the infinite charge line with charge density, linear charge density lambda at a distance equal to r. So we can substitute there any distance we need to determine, where we need to determine electric field vector. So it will be lambda 2 pi epsilon 0 r. And we can represent this result also in terms of Coulomb constant. Will be 2 Coulomb constant times lambda divided by r. So this is equation which gives the electric field an option to calculate electric field next to infinitely long charged line, and we can get to this answer with quite easily, only because of the applying the Gaussian law and taking into account the symmetry of this particular case. So next example will be surface distribution of electric charge. As you remember, we did something similar previously on our previous lectures when we calculated electric field next to a charged disk with certain radius. You can maybe remember that we had to integrate over surface, assuming change of radius from the center of the disk and also change of angle theta, which allows us in the cylindric system of coordinates define some surface area element, and then we had to integrate over radius and over this angle theta. So it was quite bulky calculation, and let us consider how we can deal with this task by applying Gaussian law. So let us consider some infinite electrically charged surface with the surface density sigma. Let's assume that it's positively charged surface. And in this case, electric field vectors will be aligned perpendicularly to the surface of this infinite plane. So we will have one vector going this direction, one vector going other direction. So these are vectors of electric field, which are or electric field lines that will be parallel, which originate at this positively charged infinite plane. So taking into account the symmetry of this problem, we also can pick up some cylindric surface. So let us draw it here on the on this surface. Let me delete maybe it's writing to me. So we pick up some cylindric Gaussian surface, and the same half will go in other direction. I can delete this field. So we have such a closed surface around this element of surface. And in this case, we will consider only electric field flux through the edge sides of the cylinder, because here we have normal unit vector and electric field vector, they are parallel. In this case, if we consider some element of surface on the side, surface of the cylinder, the electric field vector will be perpendicular to the normal unit vector. And that means that there will be zero electric field flux through the side surface of this closed cylinder surface. So we consider only this edge surfaces of the cylinder. And in this case, we can write this expression for the electric field flux in a very simple way, taking into account all these considered symmetry features and constant electric field next to infinitely large charged surface, that it will be equal to 2 times E times area. So 2 counts because we have two sides, like edge sides, and we need to take both into account. And this A is area of the side surface of the cylinder. And this is equal to the electric charge enclosed in this Gaussian surface. And this is nothing else as because we have some sigma, like some surface distribution of electric charge, then we have electric charge enclosed in this surface is sigma times A divided by epsilon 0. So from here, we easily calculate electric field next to such infinitely large charged surface as sigma divided by 2 epsilon 0. And these final equations, please write them somewhere down and try to remember, because definitely you will need these equations quite often over time to solve different type of problems. So electric field next to different continuously distributed charges, these equations which we derived here, they will be used quite often in future, so better try to remember them. So if you remember, at the end of the solving that problem for finding electric field next to a charged disk, when we did it step by step without using any simplifications and techniques like Gaussian law, assuming that distance is very close to the surface of the disk, which is much, this distance to the point where we calculate electric field is much smaller than the radius of the disk, we could simplify final equation to this form, as we got here for infinitely large plane, charged plane, calculating its electric field by applying Gaussian law. So in infinitely charged electric, infinitely large charged plane, it doesn't matter at which distance we are from the plane. This is kind of important moment. You see that here we don't have any distance in the final equation. Doesn't matter at which distance you are from the plane, the electric field will be constant and uniform all over this infinite plane. And if you have some practical, not in, usually, of course, we deal with not infinite. Sorry about this. If we have not infinite in real life situation, but the point where we calculate the electric field is very close to the surface, it doesn't stop. Then we can apply also this equation for the which we derive for the infinite electric field. Okay, pretty much we are done with all examples we wanted to consider. And now we can switch to another topic, which is conductors in electrical equilibrium. So I mentioned previously that there are different types of materials in terms of their electrical properties. For instance, most common conductors are considered metals, and metals possess free electrons which can move in space when there is some electric field which causes this motion of electrical charges, in particular electrons for conductors. However, in this topic, we are particularly focused on the conditions of electrostatic equilibrium. And in order to deal with this topic, we need to first define what are the conditions for electrostatic equilibrium of conductors in electric, which are located in some external electric field. So first one should be the fact that electric field inside a conductor is equal to 0. So this is quite obvious requirement, because electrostatic equilibrium assumes that there is no net charge transport, like movement of electrical charges inside the conductor under this electrostatic equilibrium. So net charge movement is equal to 0. So if there is no net charge movement inside conductor, then inside this conductor electric field should be equal to 0. And we will discuss this a little bit more in details. And now let us go for the second condition. If a conductor is electrically charged and it stays in the electrostatic equilibrium condition, then this charge which is placed on the conductor should reside on the conductor's surface. Charge on the surface. This also we will discuss the reason for that. The electric, like now the third point, which is required for the statement that the conductor is under electrostatic equilibrium condition. If it is charged, of course, the electric field of at a point just outside of charged conductor is perpendicular to the surface. So if we have some surface of electrical conductor which is charged and stays in electrostatic equilibrium, then electric field vector is always perpendicular to its surface, like next to its surface, close to its surface, and its magnitude is sigma divided by epsilon 0. Sigma, as this is surface density of electric charge distributed on the surface of this conductor. So the last point which should be satisfied, this condition which should be satisfied, is that surface charge density is the greatest at the locations where like surface charge density is sigma. So depends on the shape. If it's not symmetric, some random shape conductor, then this sigma will not be constant, and it will be its surface density of electric charge will be the highest in the area where the radius of the curvature of the surface will be the smallest. So actually, in other words, where will be some sharpest area of the surface, there electric surface density of electric charge will be the highest. And this particular condition we will not consider in the scope of this chapter, because it will require some additional concepts which we are not familiar with. But first three we will consider right now in more details. So let's start from the first, and this requirement of electric field equal to 0 in the volume of a conductor which stays in electrostatic equilibrium condition. So let's assume that we have some piece of metal placed in uniform electric field. So this is external uniform electric field. And we put some metal inside it. Any ideas what is going to happen in this, let's assume some very instantaneous moment at the beginning when just we put this conductor, which is not charged, just piece of metal in external electric field. Do you have any ideas? There will be some interaction with external electric field. And what should interact with the external electric field? We know that there are free electrons in metals, and these electrons can move within the volume of the metal. Obviously, if we place this metal in external electric field, very quickly, within so-called Debye relaxation time, which is reversely proportional to the conductivity. So metals possess very high conductivity, and that's why this screening time of external electric field is very short. It's around 10⁻⁶ seconds, so we can claim that it happens just momentarily. Electrons will experience some electric force because the charges which are located in external electric field, and they will be moved to accumulate at one of the side of this metal. Obviously, since initially it was electrically neutral, the other side will be, here will be some uncompensated electric charge of ions which are in crystalline lattice of this metal. And obviously between these negative and positively charged sides of the metal, here we will have some internal electric field. And you see that this internal electric field is aligned opposite to the external electric field. So means that it will kind of compensate external electric field inside the piece of metal. And once this rearrangement of electric charges has happened, and this happens in very short time frame, something 10⁻⁻15 seconds or even faster, then this rearrangement will happen until then when internal electric field will fully compensate external electric field, and we will have internal electric field equal to 0 because two electric fields, external and internal, will compensate each other. And if it is not true, so this is the mechanism, like physics behind it, what is happening in the metal when we place it in external electric field. If it's not true, and we claim that internal electric field is not equal to 0, then there will be some electric force acting on electrons or other charges, but for metals it's this electrons. And this is equal to, this electric force is equal to charge times electric field vector. And obviously these electrons will move with certain acceleration because some force is acting on them according to second law of motion. Oops. So A acceleration will be electric field force, like electric force, divided by mass of electron. And this will be Q E internal divided by mass of electron. And by definition of electrostatic equilibrium, there should not be any net transport, any net movement of charges inside the conductor and the electrostatic equilibrium. That's why this acceleration should be equal to 0. And that means that internal electric field should be equal to 0. So this is the explanation of this first necessary condition for electrostatic equilibrium. And now let us consider the second one. The second one states that if a conductor is charged, then electric charge is located only on the surface of this conductor under equilibrium, electrostatic equilibrium condition. In order to prove this, let us choose some Gaussian surface just a little bit smaller than the conductor. So it's located inside it. We already know that internal electric field inside the conductor is equal to 0. And we know that electric field flux is electric field times dA integral all over the surface. But if electric field is equal to 0, then this integral is also equal to 0. Means that electric field flux equals to 0, and that means that inside this Gaussian surface, closed surface, which we have shown on this image, there is no charge. So Q internal is equal to 0. So in all this volume, since we don't have any electric field flux according to the Gaussian law, this closed surface doesn't enclose any electric charge. Means that all electric charge which can be placed on this conductor under electrostatic equilibrium condition will be always residing on the surface of this conductor. Okay, so one more thing which we need to consider. Let's go to another slide. The fact that electric field next to the surface of a charged conductor under electrostatic equilibrium is equal to sigma divided by epsilon 0. So let us assume some conductor in electrostatic equilibrium. So we have some charge on its surface everywhere. And now we can select some Gaussian surface, which goes inside the conductor, half of this surface, and half of this surface is outside. So we have some area of this edge surface of the cylinder. Let's call it A. We have electric field, which is perpendicular to this surface and perpendicular to the surface of the conductor. And the same direction, we have normal vector, unit vector to this surface. Since electric field vector is perpendicular to the normal surface, normal vector to the side surface of this cylinder, there is no flux, electric field flux through the side of the cylinder, and that's why we should have only electric field flux through the edge side of the cylinder. But here it's important to underline that, as opposite to the previous example, when we considered infinite large electrically charged plane, we have flux only from one, like through one edge side of the cylinder, not through two, because the second one is located inside the conductor under equilibrium electrostatic conditions. And we know that internal electric field inside the conductor under these conditions is equal to 0. If it's equal to 0, that means that here we don't have any electric field for this particular edge side of the cylinder. And that's why a full flux of electric field is going through only one edge side of the cylinder, which is located outside of the conductor. And in this case, we can write that the flux of electric field is equal to integral over area for product electric field and dA. This is equal because we have, it's close to the surface, we have a constant electric field, and we know the area of this edge surface of the cylinder is equal to, according to Gaussian law, Q internal divided by epsilon 0. And this Q internal is defined by the area of the edge side of the cylinder times sigma, like surface density of electric charge distributed on the conductor, which stays under electrostatic equilibrium condition. Sigma times A divided by epsilon 0. So from here, we can write that electric field next to such a conductor under electrostatic equilibrium condition is equal to sigma divided by epsilon 0. So we don't have these two in the numerator, and that's the way how we explain the third condition for the electrostatic equilibrium of a conductor. And the fourth one will be explained later when we go through the electric potential, and then we will operate with more concepts which can help us to describe this condition in a straightforward way. Okay, we are done for today. Thank you very much for attention. If you have any questions, you're welcome. Or also you can ask on at the beginning of the next lecture. Okay, then if there are no questions, I wish you good evening. Take care and see you next time. Bye-bye.